So now that we have this definition of a limit and left-hand limits and right-hand limits and infinite limits, we can use this definition to define a class of functions called continuous functions that are really going to be our focus through the rest of the class, right? And I've got some examples here of functions that are not continuous, functions that are discontinuous, and one function that is. And I want to look at the different ways a function can be discontinuous, because then we're going to try to word our definition of continuity in a way that excludes these problems that we've identified. All right, so this function here on the bottom left, this is the continuous one. There's no gaps, there's no holes, there's no skips. And you kind of saw what I just did there. One way continuity is kind of described as, if you're looking at the graph, you can put your pen down and sketch the entire graph without ever having to pick your pen up. But that's what we mean by continuous. Now I've got several different kinds of discontinuity here, right? If you look, let's start at the bottom right. This function has a problem at x equals 0. It's got this giant gap. It's taking off down here towards negative infinity, and then all of a sudden it reappears up here at positive infinity. And the problem here is the function isn't defined at x equals 0. Right? So that's something we're going to have to take into consideration when we're forming our definition. Now over here, this is the graph of the f of x equals the absolute value of x divided by x. And I can fill this in a little bit. Let's say I define it here and I put the open circle here. Okay, now the way I've kind of redefined this a little bit, this function is defined everywhere, but it has this jump, right? It has this jump, and that's something I want to rule out. And what I want to kind of observe about this is, with this function, the limit as x approaches 0 from the left and the limit as x approaches 0 from the right aren't the same. The function doesn't match up, if you will, at those points, at that point. All right, and this last one over here. The function 2 is where the problem is occurring, right? There's a gap there. Okay, the function is defined at 2. It's equal to 4.5, it looks like. And the limit as x approaches 2 exists, right? From the left-hand side and the right-hand side, the function is kind of coming in to that same point, but that limit, the limit at x equals 2 and the function value at x equals 2 don't match up, right? That's also something we're going to have to consider in our definition. Okay, so we've got 3 kinds of discontinuity here, and these kinds have names, right? This kind of go into the same order. This one down here, this is called an infinite discontinuity. This one here is a jump discontinuity, and this last one is a removable discontinuity. It's called removable because in theory I could fix this just by moving that point down and filling in the gap, right? So 3 different kinds of discontinuities. Okay, so here's our definition. Yeah, I know there's a lot going on here, and just kind of be forewarned. This whole lecture is going to be very information rich. There's going to be a bunch of definitions, a bunch of examples to illustrate these definitions. So just kind of pause when you need to, right? Doesn't hurt to pause and take a minute and read through and think about things before and after my explanation. Okay, so the first definition, this is our core definition of continuity, right? A function is continuous at a point C if and only if the limit as x approaches C is equal to f of C. Okay, so we're going to look at more detail of this in a minute, but look at some of the implications here. This implies that the function is defined at C. If C wasn't in the domain, then f of C wouldn't exist, right? Talking about this limit as x approaches C, if that limit exists, then the left and right hand limits are equal, right? So that's going to kind of help to rule out our jump discontinuities. And finally, the two have to be equal, which is going to eliminate the removable discontinuities. And these right and left continuous, a lot of what we do here is going to mirror the things that we talked about with limits. So when we talked about limits, first we had a limit, then we had limits from the right and limits from the left. Well, it's the same thing going on here, right? It's the exact same thing. A function is right continuous if the limit as x approaches C from the right equals f of C. From the left may not exist, right? It may not be continuous on the left-hand side. And here it's left continuous if the left-hand limit is equal to f of C. Okay, so let's look at an example, right? It's kind of a wonky looking function, but to illustrate all of these issues in one graph, it's got to be a little weird looking. So you notice what I've done over here. I've got a checklist to see if a function is continuous at a point. These are the three things you need to look at, right? Take each one in order, and if all three of these are true for your point, then the function is continuous at that point. All right, so let's take a look. Okay, first, this function is clearly discontinuous at x equals -1. There's a hole there, right? There's a gap in the graph. The function isn't defined at -1. So x equals -1 fails this first test. Function isn't defined there. Okay, so how about x equals 2? Don't put it there. It's going to get in the way of 3. When x equals 2, well, over here, the function is defined at x equals 2, right? So we don't have a problem there. But let's see. What about the limit? The limit as x approaches 2 from the left is -2, but the limit as x approaches 2 from the right is 0. The left and right hand limits are not the same. Therefore, the limit as x approaches 2 does not exist. So at x equals 2, criteria number 1 passed, but criteria number 2 was not satisfied. All right, and finally here at 3. Now this time, the limit as x approaches 3 does exist. This limit is equal to 2, right? The function is approaching 2 on this side and 2 on this side. However, f of 3 is looks like about 4.5. It's not equal to 2, right? So the limit does not equal the function value, and criterion 3 fails. Okay, so you see how we could use these criteria, right? This is a little quicker sometimes than just using the definition. I like a checklist, right? We can just go down 1, 2, 3, see if any of these fail, then the function is discontinuous at that point. Okay, so this is discontinuity, right? I found all the points where the function is discontinuous. So the functions that we're going to be interested in, they're continuous almost everywhere, right? Continuous functions are going to be the interesting ones for us, for the most part. So when we talk about where a function is discontinuous, we're going to be referring to a list of points. When we talk about where a function is continuous, we're going to be looking at intervals, ranges of numbers. Remember, just like always with functions, when I want to describe where a function has a certain behavior or a certain property, I'm going to do that in terms of x values. All right, so you see, I've got this definition here. Right, let's go over this real quick. A function is continuous on an open interval. Remember, an open interval looks like this. So interval for an open interval is one that doesn't include its endpoints. If it's continuous at every point on the interval. When we talk about closed intervals like this one, where the endpoints are included, then we're going to say it's continuous on this interval if it's continuous at every point in the interior, left continuous at the left side, and right continuous at the right side. So I could say my function here, for example, is continuous on the closed interval from x equals 0 to x equals 2. Because it's left continuous here, it's right continuous here, and it's continuous at every point in between. Okay, so if I wanted to describe just overall where is this function continuous, then I would say we start at -2, and it is left continuous there. I always have to stop and think left and right. It's left continuous at -2 up to -1, and all I'm going to do here is I'm going to exclude -1 up to 2. I'm going to exclude all of the points where we previously saw that the function was discontinuous, 2 up to 3, and then 3 up to 4, and I'm going to include 4 because it is left continuous at -2 and right continuous at 4. So this is where the function is continuous. All right, so that gets a little old writing out these lengthy unions of intervals sometimes. So I want to be able to generalize this. I want to be able to talk about a continuous function, right? The function as a whole. And the way we define this is it's very straightforward. A function, a continuous is one that's continuous at every point in its domain. And a function that's discontinuous is one that's discontinuous at one, little typo there, one or more points in its domain. Now this domain thing, this is a little interesting because we take some shortcuts when we're teaching algebra classes and pre-calculus classes. Technically, to define a function, you have to do two things, right? You have to define the function itself. You have to give a rule or a formula, right? And you're supposed to also define its domain. And we don't usually do that. Right? We don't usually do that. For example, if I were to ask one of my college algebra or pre-calc students, what's the domain of the function f of x equals 1 over x, they would say, well, this is all real numbers except 0, because we are thinking about rational functions. You have to include any value that makes the denominator 0. Okay. And that's fine. I'm not saying we shouldn't do that, but I could define the domain of this function to be something else. I could define the domain of this function to be all positive numbers, right? I can define the domain to be practically any interval I want it to be. Okay, so what we're going to do, because I don't want to replace what we've done, what you've done in previous classes. In algebra classes, when they say what's the domain of a function, usually what they mean is what's the biggest possible domain, right? What's the most inclusive one? And we're going to continue that. It's often called the natural domain, right? It's the largest set on which the function is defined. Okay, because this creates some interesting situations for us. Take a look at this function. This is our old friend f of x equals 1 over x. So let me ask, I want you to really think about this for a minute. Is this function continuous? Okay, see, that's a question that we can't on its face answer, because you have to know the domain, right? If we take the domain to be this natural domain, right, everything except 0, then the function is continuous. Right? The answer to that question is yes, because if you pick any number from this set, any number other than 0, this function is continuous at that point. So because this function is continuous on, in this case, its natural domain, at every point in its natural domain, I would say yes, this function is continuous. Now, when you change the domain, you potentially change the answer to that question. Okay, if I said I wanted to talk about the function f of x equals 1 over x, and I want the domain to be, for some strange reason, all real numbers. Okay, this function is not continuous because it has this infinite discontinuity at x equals 0. Right, so the domain is really important to answering this question. Now, going forward, okay, let's all kind of come to an agreement here. When I ask about a function, unless I specifically say otherwise, assume that the domain is this natural domain. It's the domain you would have found if you were asked to find the domain in an algebra class or a pre-calc class. So now we've got a bunch of definitions, that nice little checklist for determining if a function is continuous at a point. So in the next lecture, we're going to continue to expand on this. We're going to look at some more ways to show when a function is continuous and when it's discontinuous. And we're going to look at a bunch more examples, specific functions, so that we can really kind of get a real feel for determining continuous versus discontinuous.